So let us look at what microarchitecture is. A microarchitecture is basically the implementation of the ISA uh, under specific constraints and goals. And these constraints and goals are basically stemming from some of your performance goals, or from your energy goals, or from some other goals that you basically have. And the design constraints, well, they are inherent in your problem because you're using electronics, and well, you cannot go smaller than some sizes, you cannot go faster than some sizes, so you cannot just say that I'm going to have a 10 gigahertz microprocessor. That just doesn't happen. Okay, or 1 terahertz microprocessor. I mean, you get some physics constraints. And I'm going to try in this lecture and in the upcoming lecture on microarchitecture, or on architectural architectures of computer systems, basically to cover a few of these things, because they actually affect performance, and they affect some of the design decisions in operating systems. So today I'm going to talk a bit about pipelining and what pipelining is. I'm also going to talk a bit about out of order instruction execution. These two basically affect a lot how the scheduling is done, and they also affect things on the threading level, as we will talk in tomorrow's lecture. There are other things that basically affect your performance when you start talking about memory and the operating system, and that basically includes memory accesses, caching, prefetching. These three will also cover to some extent in the next lecture. Then there are other things that are studied under microarchitecture and in a traditional architecture course that we are not going to cover here, because I'm not trying to give a course on microarchitecture in any way. I'm just trying to put your mindset in the why are we doing these optimizations. Otherwise, I could just go in an operating systems lecture and tell you, well, we're optimizing this because because that's how what happens when you have a pipeline flush, for example, and then that doesn't mean anything for you. Or as I was talking in during the first few lecture about the program counter, some of you have not studied these things, so although they are very easy to memorize, but I'm not sure if that is what I want you guys to take out from this course. I want you to understand why did we take these design decisions, basically, and that's why we have these lectures. But again, I advise you to basically take a look at the lectures from Carnegie Mellon. They are available in video, and they are pretty good. And there are a few very good books on the topic, and I think you probably can ask your colleagues from the engineering program, for example, what books they were using. But there is just the David Patterson and Hennessy's book on computer architecture, which is like the Bible of computer architecture to teach, basically. Okay, so when I am talking about the instruction set architecture, I talk about instructions, and I said that the instruction set architecture defines how the instructions are done, and this is how what I actually mean. Each instruction, I'm trying to get my pointer. I hope you see my pointer. Each instruction can be divided into parts. The first part is the opcode, which basically says what the instruction does. It's basically like having if is a keyword in C, Java, in any programming language in the world, right? So if is an if statement is you use it, right? So this is the statement name, if. The opcode is basically the if. It basically defines what are the instructions that you can do on this processor. And then you have operands, which are basically things that you operate on. An example for this, for example, would be an opcode that basically loads something from memory. And then what you would need is basically operational code and the memory address. And then you might also want to have a destination address, but you might have a general purpose register that basically stores whatever you do from as a result from this. And I have to say that this is how the alpha instruction alpha is a type of processors. And this is their instruction set architecture basically. And you can see that it's divided into different parts, and there are different kinds of instructions. Some of them are just opcode and some number, some others are opcode and some registers passed as parameters. These are your parameters. And then some are opcodes and two registers, your parameters, and some are opcode and two registers and a function and another register. So I mean, you have these different kinds of commands, which is just like saying, it's equivalent to saying that an if statement would take a condition as an input, right? So you have if statements that take conditions as inputs. And while you might have other statements in programming that that takes other things. So, for example, a print statement would take a string input, for example, and this defines what a print statement is. But also you have things such as or, which is a keyword in most programming languages. So if you say that condition 1 or condition 2, this is this basically evaluates the right hand side, the left hand sides, compares them, and sees if any of them basically is happens, right? So you can have statements that take two operands, and that would be, for example, something like or and two operands here. Okay. This is the ARM instruction set architecture. Again, you have you have some flags, you have an operational code, you have some registers, and you have some operands basically. And yeah, we're not going to go through this. You can go to search for the ARM instruction set architecture. It's published online. It tells you what are the different commands, and it also tells you what do they evaluate to when you start evaluating them into numbers basically. Okay. So when you do instruction processing, there are a few things to note, that there are different styles to doing that. Okay. One of them is that you have some instructions, as we said, that has zero addresses. Basically, it doesn't take any operands as an input, and that would be basically something like push, where you basically push stack, or pop stack. I mean, you do not operate on an operand. You have you basically give the instruction the stack number, but you do not have something that changes. You do not change a here. So push a here, for example, does not change a. It just pushes something in the stack. Okay. But you have also one address instruction processing, which things such as an accumulator. So when you have I++ in whatever language you like to use, you have a similar thing in assembly language. You have things such as two operand machines, which take basically two operations, two inputs. For example, for both source and destination. So you operate on the source and you save your output to a destination. And x86 is a two address machine actually. So and then you have a three address machine where you have three operands, and you basically have an operation, a source 1, a source 2, and a destination registers. And there are trade-offs between all of these. With a zero address machine, you can do very limited things, because you can basically do things. So you can shift, for example, 1 bit, okay, but you cannot do anything more than that. And to do additions and multiplications is just a mess. One address machine, again, you can have an accumulator that you accumulate to, but you do not have really the possibility to do a lot of complex instructions, and so on. So there are multiple trade-offs. And larger operate instructions versus more executed operations. So do you want one large command, or do you want more operations that execute very fast? Code size. So if you have a zero address machine, zero address stack machine, then the code is large. But but the execution time will be quite fast because it's actually not complex at all. Versus if you have a large something with 3 addresses, then the code might be smaller, but it takes more time to execute the commands.